Let's talk about filters. Analog filters are made with capacitors, condensers, and resistors. The impact of a capacitor on an electric circuit is changing the phase on a frequency-dependent way. This means that the delay is frequency-dependent, not like a classical delay line where all the frequencies are delayed by the same amount. Here it's different. In the analog filter with the condenser, time shifting, the phase shifting, is frequency dependent. The phase difference between all the harmonics, between all the frequencies, is the same. This is how we can achieve to change the tonal balance with filters. Filters are, in fact, simply phase devices. Of course, there are linear phase filters, but let's talk about a traditional type of design. Many digital filters just mimic the same design and reproduce the same impact on phase as analog filters. I'm going to show you something funny. Let's dial in a FabFilter Pro Q4. I have some white noise playing. I'm adding my device on it, which is a Pro Q4. And as you see, I dialed in an all-pass filter, which is a specific type of filter that is not affecting the sound, but just the phase. Now I'm flipping the polarity of the signal and I'm adding this to the dry signal. So basically what's happening is that everything that is the same between the two signals will get removed. And so everything that is now the same without the effect of the filter, because it's flipped in polarity, will now be inversed from the dry signal. So they will be subtracting, while everything that has been shifted in phase will remain. Let's listen to that. Oh. I created a filter. Now you can see the impact of the slope of the filter. How many decibel per octave? 6 decibel per octave gives you a 90 degrees shift. Here we have plugin doctor showing us the phase effect of a filter turned on Pro Q4. So as you see, the plugin mimics the behavior of an analog filter by having a frequency dependent delaying. A detail here is that plugin doctor is showing the shift of phase in a radiance. Zero radiant and at 3.14, which is pi, so it means that there is a shift of 180 degrees when we get there. So from no phase rotation at all, it starts to rotate. And of course, we can only go back in time. We can't move to the future. We can't predict a sound that hasn't been played yet. So filters and the effect they have on phase will always be to look back to what has already been made. This is why the shape will also be like this. You couldn't have a shape where it will go up like this, because this would mean that we would go forward to time. We will be in the future before the present time will have happened. And this is one of the specificities of the Isotope RX tool. It can go to the future. It can move things in both directions, while processes that are applied real time, of course, they can't. The cutting frequency, here 500. And at 500 we are just at half of pi. So this means that we have here 90 degrees of shift, and 90 degrees of shift result in a dip of 6 decibels. A higher cut will induce a stronger phase shift. 6 decibel per octave induces only a 90 degrees of shifting, hence a very slow slope. The sum of two exactly similar signals produce an increase of 6 decibels, minus 12, minus 12, minus 6. The sum of two exactly out of phase signals results to silence, and the sum of two signals that have a quarter of rotation of phase results in a difference of 3 decibels. And so you have only a difference of a reduction of that signal by 6 decibel per octave. If I have stronger filtering, 12 dB, I'm adding another 6 dB. Now I have a total flip at the cutting frequency. Steeper slope. Even higher, now I see I am adding, every time I'm adding 6 decibel per octave, I'm adding actually 90 degrees of flipping. And as you know already now, at 180 we are at total inversion. And so now we are at 270, so we have 18 decibel by octave from this corner frequency. And of course, the Q is pushing the resonance because the flip is happening in a steeper way, right? The great thing about this new addition of Pro Q4 is that we have not only the all-pass filter, but it has a selective slope. You can dial in very, very in detail slope. So we have, in fact, a device that allows us to retune somehow, to rephase things if there are phase issues between elements in a very, very clinical way. Wider, closer. It might sound silly to recreate a filter with a filter, but you see that now you understand deeply that your filters are only phase shifting devices. We sum something that is shifting the phase, we flip the polarity, with something where we keep the dry signal, and only the phase interactions between those will give the remaining sound.